Well, welcome, welcome. We are so excited to finally to meet with you today. For our audience members, please introduce yourself and share with them a little bit about who you are and how you came to be involved in space.
I am Hava Turkakin. I am from Turkey. I had my bachelor in physics and I did master's and Ph.D. in space physics in University of Alberta, Canada, which is where I got involved in space physics. And it's a funny story. Actually, I was planning to work on black holes and so all excited topics in research, but all the researchers were picked up already. They had a lot of students. They couldn't take me, and I went for space. I said, it's close enough. And I became to love it more than the other subject areas in astronomy and cosmology. I love it, and I kept working on space.
What are some themes? So most of us know physics when you're an undergrad or a student, even pre-college, you know about mechanics and forces and energy, electricity, magnetism. How is space physics a little bit different or the same from sort of some of the standard topics that you might see in a physics class?
I actually I had no idea there was a subject like space physics. I didn't know what plasma is. I was quite blind about how exciting this area could be. I took astronomy classes, but nobody even talked about plasma in there. We have all these star evolutions, black holes, and so on and so forth. So I had no idea. I couldn't connect in the beginning. I was like in a totally different area than physics, and I slowly start to pick up that it's really deeply related to particles, deeply related to electricity and magnetism, and how those particles interact with magnetism. I get to understand it better, and the more I understand, the more I figured out it's really exciting area, and it's really deep physics, not really a different thing. It's all physics, but we just undergraduate level courses, unfortunately, are not very common, and I would be really interested in opening one here.
So you're one of these folks that might see a star, and whereas we just see a ball of gas with light, you see almost a living thing, right? A very dynamic,
See, that's what I was trying to figure out, like, how the plasma part fits in, because just like you're saying, I mean, I've heard of obviously black holes, but I can't even fathom plasma. So it's the reaction to what we're seeing.
I'll let the doc explain it.
It's actually exactly when I see a star. Before I took any space physics course, I was thinking, okay, ball of gas and dust and just staying there. And so now I see an alive plasma having particles going around magnetic field, shooting some of it out, and it's all active. It's very different. It's very different than what I knew. And as I know, black holes swallow and everything, I didn't know it's actually swallowing parts of the stars, which are plasma and emitting light as they go in. I don't know why astronomy is not involved in some of that. I did not have any information about how plasma is actually in the heart of the stars and how they work, which should be in astronomy books as well, but I don't know. Maybe it's too much.
Is it kind of like a recent thing where technology advanced enough to be able to determine that it was there? I mean, how long have they known plasma was part of what we were seeing?
I don't know. A lot of researchers I talk from astrophysics mainly say they are working on plasma, but it's, well, not real plasma. They are working on the stars and so on, as they assume they're just particles floating around like a fluid. While in plasma, we put the magnetic field, which is the general complication that we should have there to make it correct. So I believe still to this day, they're not really involved in plasma as plasma in their studies, unless they are specifically studying on the sun or the solar wind of other stars. They don't involve it as a plasma. They involve it as particles freely rotating around or going around without magnetic field, which is actually not even correct. I don't know.
I always find fascinating the fact that you have this fusion going on and this immense pressure and immense temperatures, but at the same time you have gravity fighting it. So the star is constantly in this dance between wanting to expand and its own mass causing it to collapse. I find that very interesting. Could you share a little bit about your thoughts on the connection between or how the size of a star is related to those different forces?
Oh, actually, this is more like, again, this is more like astrophysics side, I believe. How stars forms, and as they form, gravity collapses them down. As the gravity pushes the particle closer and closer, at some point they heat up, and at some point they are hot enough to start fusion. And when they start fusion in them, hydrogen turn it into helium first. That fusion try to expand them, and gravity keeps pushing down, so they have an equilibrium until their source of fusion ends at some point. So all hydrogen converts to helium first, so we have a stable like star, and as the fusion happens, it emits energy, and that energy comes out as particles going out with the magnetic field and so on, which is plasma. So that's, I'm studying what happens outside of stars as that energy comes out. But that's what is happening in the stars. And after hydrogen fuel burns and finishes, then helium converts to carbon. And after hydrogen finishes, star collapses a little bit because we have now helium that is not hot enough to have fusion. So we don't have helium fusion, star keeps collapsing. At some point, it's hot enough to start helium fusion. And then it stabilizes again because this fusion keeps it stabilized. There's gravity, there's fusion keeping them stable. Helium converts to carbon, I believe. I don't remember exact sequence,
No,
but
it's very complicated. It runs all the way
going.
to iron, right? I think
Yeah, until the iron, this sequence keeps going. Carbon burns into another one and so on. After iron, it's too heavy to collapse enough to burn and start fusion. So star's life finishes. And
Well,
how it finishes depends on how heavy it is, perhaps everybody.
Yeah. Well, let's flip back to your happy place and talk about plasma.
Wait, before you go, I want to clarify something she
Okay.
said, please. So for the layman like myself who might be listening, right? So it sounds like the difference between astrophysics and space physics, from what you said, is that you're studying outside of the stars.
Yeah, either I'm studying the outside of the star, how it emits its energy, how that energy, or I'm studying how that energy is traveling in the space and how it affects whatever is in there, the
Right.
planets, the moons, and everything. That's what space physics is. It's mainly around the solar system, but some part, it goes a little bit into planetary science, but some people works on other habitable planets and their stars. That's also similar topics. Yeah.
So one way you might characterize it for the layman is you're sort of like into space weather, at least the
exactly
things that emanate from the star and how they interact with the environment around it.
Yeah.
I thought we might circle back to plasma. Have you had the chance to work in labs where you created plasma or go visit and work? Is there an easy way for a scientist here on Earth to directly create and manipulate plasma, or is it best done indirectly through observations with telescopes?
There's a way to create plasma, which is actually done in the labs. A lot of plasma physicists are actually, that's a different area, close to space physics, but different area. They are working into generating plasma and generating fusion on Earth, which is another area of research. So I didn't do research on that. I had a friend working on it. So as far as I know from talking to her, is they send laser light through particles, and that very energetic laser light generates a plasma in the column they send it, and they have a plasma there. They study that. They study how it interacts with the surrounding, and mainly, again, they try to see if we can energize particles to a high level enough to generate fusion.
Right.
It's not achieved yet, but it's a research people
It's
are.
the hope for clean energy in the future, right?
Exactly, yes. It's the
Right.
hope for clean energy in the future.
And for our listeners that may not be scientists or engineers or even young students, think of plasma as a really energetic state of matter where the electrons have too much energy to remain around a nucleus. And so I always describe it as a hot and pressurized soup of particles. Could you please correct my analogy or maybe improve on it?
It's actually correct. I actually describe it in any level of course I teach as the fourth state of matter, where we have very energetic electrons that are not able to stay tied to protons. So we have actually a gas that is totally ionized. The protons and electrons are flowing around, or it could be a gas, oxygen gas, let's say, but lost some electrons, it's ionized. There is no full atomic gas in there. Then we have a plasma. So your description is totally correct. And I believe we should teach plasma as the fourth state of matter in elementary schools even. It is the fourth state of
Well,
matter.
I can tell you this, in sixth grade, the questions they will be assessed on is, what is the most prevalent state of matter that we know of in the universe? And that, of course, is plasma.
That is plasma.
Such a high percentage of our solar system, right? Is it probably 98, 99% of
99% of the universe is plasma.
sun.
Yeah.
So,
Well, since we're talking about the sun, I noticed that, when I was recording the bio, your research area was in solar-terrestrial, right? So between the actions in between. So is that what we're talking about here? Is like the energy that's kind of coming out from the sun and how it kind of influences the other planets or things like that as well? And you can actually, is that the plasma? It's something you can measure in between that energy?
Exactly. We work on, I specifically work on the solar-terrestrial interactions. A part of it, if you want me to go more specific, I could, but I'll be more general here. We have a lot of spacecrafts in between the Earth and the sun, measuring the number of particles, their temperature, how many and how energetic they are, density of the plasma coming in. And on Earth, actually, NOAA itself uses that input to give us information about the weather on Earth, because this is where it starts. So space weather is directly connected to the weather on Earth. How energetic those particles are important in how much of them are escaping, coming closer to the Earth and affecting the life on Earth and weather on Earth. So we have a lot of spacecrafts measuring those. We have a lot of spacecrafts measuring what happens after that, closer to the Earth. We look at all those data and try to understand what happens here as the solar wind comes in, what happens closer to the Earth, and how they could be connected, which is quite related to what I do as a research.
Well, wait, Kevin, so I'm trying to understand, right? So with the solar sails, like on CubeSats, when they use those, is that harnessing that energy that she's talking about to use as a way to move through?
Solar pressure, yes. If you have a very light spacecraft and you don't have to accelerate it in a hurry, you can certainly use the energy, the particles and the waves of the sun to exert a force on your sail. Yeah. I wanted to share, and I'd love for you to elaborate. If we get a little bit of solar activity, we get beautiful northern and southern lights. If we get a lot more solar activity, then we lose the internet and we electrify our grid gets, our electrical grid falls to pieces. Maybe you could elaborate on, because I had read an article that, they're sort of thinking we might have some intense solar activity that might affect the Earth. So maybe you could just share a little bit about, we take it for granted the sun's always going to be there, but it does things that could really be dangerous to us as here on the Earth.
Yes, exactly. So main hero of the story, I believe, is the magnetic field of the Earth. The sun is always there. Sometimes it sends intense number of particles with high energy flowing fast. And the Earth's magnetic field is the one that deflects them around, because those are all charged particles. And as we know, charged particles deflects around the magnetic field. Magnetic field pushes them around. So it doesn't let them come closer to us. And it forms a protective bubble around the Earth, what we call magnetosphere. However, if the particles are energetic enough, some of them can escape. And where they can escape is mainly the polar regions, because we have particles circling around the magnetic fields and they can rain down into the atmosphere, which is what we call northern lights. If they are very energetic, they can rain down closer to the Earth. They can cause a lot of grid destructions, electricity cuts. Polar aviation is affected from it, even pipelines on the surface of the Earth, depending on how strong they are and how strong energy they have. What they mainly do is they affect the Earth's magnetic field value, generate currents. And those currents feeds into the system we have and disturbs our systems. There are events like causing worldwide, not worldwide, but blackouts in certain regions. There's one, the famous one is 2003, I believe, what we call Halloween events, and it caused really wide blackouts in northern Canada, I believe, because northern regions are more vulnerable, but it could move down depending on the strength.
So while you're a space physicist, you're also interested in and study the relationship between the solar weather and the Earth, at least the Earth's magnetic field. Is that a true statement?
Yes, that is a true statement.
So I didn't read I read an article recently, or at least I read the heading. Let me be honest. I read the title of the article, but it had something to do with why the Earth's magnetic field is not uniform. And there's a place, is it in the Atlantic? Is it where the South Atlantic anomaly is that the magnetic field is weaker? I wondered if you had spent any time with that.
No, actually, honestly, I don't have information on that.
That's fine.
It's close to the surface of the Earth, I assume.
Yes. It's
The Earth's magnetic field is not constant by nature. As we go farther away from Earth, it changes.
Sure.
And it's a very volatile change in value, in direction and magnitude already. Another thing I can say is, as the magnetic field of the Earth, of the sun comes and hits the magnetic field of the Earth, a lot of details happens there. And sometimes, depending on their direction, these two magnetic field lines combines, we have a total magnetic field line. Then we have a lot of changes happening in the magnetosphere. Different regions forming, magnetic field change in direction of magnetic field change, and different flow of plasma escaping towards the Earth. A lot of stuff happens. I don't know how much details I should go in here, but
well, he's drawing pictures of everything that you're saying over here, so that's why he keeps trying to bring it down to my level. He's drawing.
Okay. That's a good picture.
I was just showing how the particles don't get a straight line path to the surface of the Earth, that the magnetic field lines just, they change.
Exactly.
But we could be overpowered. Our magnetic field is not impervious to the, what could come from the sun. So
when you talk about bit flips, does that have anything to do with the solar, the radiation that's coming from that?
It really, we get concerned about bit flips in our spacecraft. Especially, it seems like they occur more often in the South Atlantic anomaly. So that, I think, is a function of having a lot more charged particles where our spacecraft passes through, a more energetic part. Sometimes we get a 1 that becomes a 0, or a 0 that becomes a 1. We call those bit flips. So you have to often, if you're in a higher orbit, make sure you have software considerations to how you can recover from some interference from space weather, and how you can reset your computer. So
I believe that would be because that is a region, I'm really terrible in geography, but that is a region close to the polar regions. So that would be where those particles can easily escape, the most energetic ones. Yeah. And that
makes sense, right? If you have a low altitude polar orbit, you're going to pass through twice in orbit the most concentrated region of the particles.
Exactly. Yeah. So there are some researchers working specifically on polar caps, northern and southern, to understand that better, to help build better, stronger spacecrafts to endure that. And also aircrafts, depending on the strength, aircrafts also could be affected.
Right. Well, let's pivot to your students, your current work, and maybe how we met through a certain NASA opportunity.
Yeah, we met, Kevin and I met through what we call NASA HEAT, NASA Heliophysics Educator Activation program, I believe. Is it? No, HEAT.
Let's call it team.
Was this the one in Orlando that you went
Yes.
to?
Activation, I don't know what T is for, but we are simply space physics ambassadors. We are all interested in educating public and schools about space physics, research in space physics, how important it is in our actually everyday life. It's out there and in here. That's what I really like about space physics. If you study black holes, star evolutions, all exciting, but space physics is affecting our everyday life. It's a very important area of research, and it's really, really surprising that public don't know about it much.
No. Black holes are light years away. Our sun's only 8 minutes away.
Exactly. I was thinking before I become a space physicist that we know everything about solar system, but we don't know anything about solar system. A lot of stuff.
I'm excited for exploring the moons and, like not only going to the outer solar system, but just in general, just things to learn. There's so much we need to learn about how they formed, how they behave. Why is there liquid water, so far away from the sun?
Places.
Well, let's talk about how a student might come into space physics then. So by the time you see them, they're normally graduate students, correct?
No, undergrad students.
Oh, undergrads. Okay. So when a student, like when they're first coming, I'm just assuming our students probably don't know, just like I didn't. I've heard of astrophysics, that there's an entire separate area of study. So what kind of students would be ideal for candidates for, like, what would their interest or skill level, what should they be thinking about?
We have several undergraduate physics students. I think that should be our main, for me at least, they are my main focus point, because they are already interested in physics, and it's going to be very easy to get them interested in physics. So what I'm planning to do and doing also is to hire students. I got this NSF grant for doing space physics research in an inner area of the Earth's magnetosphere. And I'm hiring one high school student, one undergraduate physics student to work on this with me. And what I'm planning to do is actually I'm going to make them, one of their duty will be to be space physics ambassadors with me. And what we're going to do is we're going to take NASA HEAT activities to schools. We're going to show one activity, do them with the teachers, and then leave information that there's more to that. And this year we're planning to do what we have there, eclipse activities, because we have 2 eclipses coming in. It's right on the spot. They will be interested. We'll talk to them about eclipses, and we're going to have the students do that this activity, which will get them excited. And I'm hoping to get more physics students coming here and becoming more undergrad space ambassadors with me, hopefully.
That's fantastic. I worked at NSF for 6 years, and so I want to tell our listeners, it is a big deal to win an NSF grant, because they are very competitive. So congratulations.
And a lot of work. I remember.
It's a lot of work. Yeah.
It's that is not a short proposal that you knock out one evening, right?
No.
But I just want to tell you, it's awesome. We're proud of you for earning a grant, because that's a nice seal of approval on your research if the NSF is willing to support it.
Well, and I think too, what I love about what you said is you've got a university student, but you're also bringing in a high school student. And we talk all the time about how we think that education is messed up, and that we oftentimes expect students to wait until they're at the university level before we really give them the real hands-on work of aerospace. So the fact that you brought it to high school is
exactly. I believe we should even bring it down to
younger. Yeah. Well, no, I think we agree.
We're willing to come help you run a summer camp next summer. I can do orbital mechanics if you'd like. We can do some Holman transfers with the middle school.
That would be awesome. That would
10,
be
11,
awesome.
12 years old. We need them really young. If they can do pre-algebra, let's do space math.
Exactly. They can do space.
Yeah.
Please tell me about that. I'm definitely interested in.
Well, I just want to tell you, I really enjoyed meeting you. We were in a NASA HEAT workshop in July. I think it was late June summer in Orlando, and it was fantastic. And I just want to thank you for being here.
Well,
thank you for having me. I really enjoyed meeting you too.
Well, before we go, we always ask for any words of advice. So our final question for any of our listeners out there who might be aspiring physicists, or who might be the parents or educators of students in their classrooms, is there something that you want to give to them as we leave? Is it about teaching plasma, or is it beyond that?
It's actually beyond that. I want to tell them that if they are interested and like it, go for it. It's not always easy like that. They will have hard times understanding stuff, doing stuff, maybe succeeding in something they want to succeed in, but they will succeed in as long as they persevere. Perseverance is the key. Don't give up. Keep going. You'll get where you want to go.
We appreciate
Fantastic. Well, we're
This
going
is
to
awesome.
post the link to your classes or your links on our show notes, and we're also going to publish the link to NASA Heat. So Rebecca should like that we're advertising for
that.
NASA
Make sure you
Heat.
send those to me so I can get
Thank
them.
you.
Thank you so much. We really appreciate it.
Thank you very much. I appreciate it. I appreciate your time.
You're very welcome.